Welcome to video on control systems. In this video, we will have a look at stability criteria using root locus system. Before we start, okay, to understand this video, you should be knowing what is transfer function, poles and zeros, and of course the characteristic equation. How do we write the roots array of a given characteristic equation? Okay, with these prerequisites, so let us start the roots array. So now we shall consider the transfer function block diagram with GFS as a forward plan and with a unity feedback. This is RFS and CFS. So we are asked to find what is the stability of the system. Let us consider GFS as K by S into S plus 1 into S plus 5. Now if I locate the open loop poles of this system, it has got a pole at origin, there is a pole at -1, there is a pole at -5. Uh, we know that poles will start from the open loop pole position of 0, -1, -5. So starting point is 0, -1, -5. Since there are no zeros, all loci will end at infinity. So we need to have their starting point. Suppose if you write starting point of the loci is 0, -1, -5. Next is end point. End point of the loci is infinity, infinity, infinity. Third one is okay, which point of root locus is a part of which part of real axis? So the real axis of S plane is equal to root locus. Which part of this is locus? So we know that we have to just partition this. So you stand on this side, how many are there to the right? There is nothing. And if you identify this is segment 1, segment 2, segment 3, segment 4, in segment 1 there are no poles and zeros onto the right hand side. In segment 2 there are odd number, so this is a part of your root locus. Here this is a even number, 1 plus 2. Here in this S4 segment you have odd number of poles plus zeros. So we know that the direction of the root loci will leave the pole, and it is going to leave the pole. So now the direction has been put. Fourth one is direction, and the fifth one is let us look at asymptotes. Asymptotes. Their centroid is required. First is how many? How many means so we're going to have P minus Z. There are three asymptotes. Next one is centroid. Centroid will be 0, -1, -5, minus of 0 divided by 3. So it is -6 by 3, which will be -2. So we have the asymptote at -2 centroid. The angles are 60 degree, 180 degree, and 300 degree. So these are the asymptotes. So this is 60 degree approximately, this is 180, this is 300. From here to here it is 60, from here to here it is 180, from here to it is 300 degrees. Sorry, 300 degree. So now this is done. So next we need to find the breakaway point. To find the breakaway point, there are two ways, because why this breakaway point is required is these two poles are coming in opposite direction. They will going to break somewhere. To find breakaway point, so we need to find dk by ds and equal to 0. So before that, let us find the value of k now. So let me do it in another page. So this is my GFS. So GFS is equal to k by s into s plus 1 s plus 5. This can be written as k by s into s square plus 6s plus 5. So del of s is nothing but 1 plus GFS into HFS. We know that HFS is taken as 1. So then this will be 1 plus k by s cube plus 6s square plus 5s equal to 0, 0 characteristic equation. So it is now s cube plus 6s square plus 5s plus k equal to 0, 0 characteristic equation. So from this, k can be written as minus of s cube plus 6s square plus 5s. If you differentiate this with respect to s, then this will be minus of 3s square plus 12s plus 5. Therefore, roots of this would be is this second order, which is 3 equals 12 equals. Now one of the root is minus 0.472. The other one is minus 3.527. So we are looking for a breakup. This is the breakaway point. So we are getting two roots, two values of s where there is a breakaway possible. So actually, on the S plane we are expecting the breakup point between 0 and minus 1. So here this is the breakup point. So this is not a valid breakup point because here between minus 2 and minus 5 there is no root locus coming at all. So this is so it will break here. So it will break here at minus 0.472. Once it breaks, it will become complex. It will become complex. It will become complex, and we know that this asymptote will guide them to go to infinity. Before we actually draw this line, let us find the point of intersection of this root loci on the imaginary axis. Now this is because we know that this loci has to cross this imaginary axis, has to come to right side. So when it is crossing right side, it is when it is going to right side, it has to cross this imaginary axis. Point of intersection of loci with imaginary axis. Imaginary axis. So for that we need to write the root survey. So how do we write root survey? So you have this equation. So it is s cube s square. It is now 1 5 next is 6 k. And it is s over 1. It is 30 minus k by 6. It is 0 and then k. This is s over 0. So from this, so when this term becomes 0, you'll end up with the auxiliary equation. So when does this term become 0? So when 30 minus 6, sorry, 30 minus k becomes 0. That is, when k is equal to 30, this will become 0. It will end up with the auxiliary equation AFS, which is nothing but 6s square plus k margin. So this is k margin. How much is k margin? K margin is 30. So now if you find the roots of this, then 6s square is equal to minus 30, then this will become 5, then s is nothing but plus or minus of j root 5, plus or minus of j root 5. So root 5 is nothing but 2.23. So when it crosses the imaginary axis, this value will be plus j 2.223. This will be minus j 2.23. So it breaks here at 0.427. It crosses the imaginary axis at plus j 2.223, and it goes along with your asymptote. So it just crosses imaginary axis at minus 2.23 and it goes like this. So this is the root locus. So what is the stability now? The stability of the system is if the value of k, this what is k margin? So k margin is found out to be how much? K margin is, this is what is k margin we found, which is 30. So k margin is 30. So system is stable for all values of k less than 30. It is unstable for values of k greater than 30. It is oscillatory when k is equal to 30. When it is oscillatory, the frequency of oscillation is 2.23 radian per second. So this is the entire summary of this particular. So this is a conditionally stable system. Fine. So let us move on to next section. So let us take up, we have something like this. So there is a GFS which is nothing but k into s plus 1 by s square into s plus 4. If you can write the poles like this, then you have repeated poles here, and you have one more pole at minus 4, and this is at minus 1. Correct? This is what we have. So in order to write the root locus of this, so we know that loci starts at origin minus 4. Loci will end at minus 1 infinity, because 2 will end at infinity and 1 will go to 0 position. And asymptotes, okay, which part of the root locus is a part of root locus? So segment 1, segment 2, segment 3, segment 4. Segment 1 is not a part of root locus. Segment 2 is also not a part of root locus because you have even number. And segment 3 is a part of root locus. You can see this is a part of root locus. And over segment 4, segment 4 is not a part of root locus. So it goes like this. It goes like this. Correct? And number of asymptotes. Asymptotes are Number of asymptotes are p minus z, which is nothing but 3 minus 1, which is 2. So centroid is 0 plus of 0 minus of 4 minus of minus 1 by 3 minus 1. So it is now minus 4 plus 1 by 2, which is minus 3 by 2, which is minus 1.5. So you have an asymptote. What are the angle of asymptotes are 90 degree and 270 degree. So you have asymptotes at minus 1.5. It's so here and here. These are the two asymptotes. And if you can actually try to know the breakaway point, of course you can directly write, because you have repeating poles at origin, the breakaway point would be 0. The breaker point would be 0. So we can directly write that breaker point is 0 because there are repeating poles at origin. Whenever you have repeating poles at any point, the breaker point is that point itself. So it just breaks there itself. Once it breaks there, we know that asymptote is here. So once it breaks, it actually goes this way. This actually goes this way. It is as simple as this. So this roots array is over. Sorry, the root locus is over. This is the root locus. This is the root locus. How do you say this is a root locus? Because poles, this pole will going to terminate here, and this pole will going to be here. So it will actually go, these two roots will go to infinity along with this imaginary, along with this, okay, asymptotes. So it will never cross imaginary axis. To just verify what is the value of k, if you can actually find out, you will have an absolutely stable system. So if I write del of s of this, is it not s square into s plus 4 plus k into s plus 1 equal to 0, then this will become s cube plus 4s square plus ks plus 1 plus k equal to 0. If you find the roots array, then this will be 1k 4k, then frequency it is 4k minus k by 4, 0 and k. You can see this will become 3k. This will become 3k by 4. This is s cube, this is s square, this is s power 1, this is s power 0. So now you have the first column as 1, 4, 3k by 4 and k. This is the first column because we are interested in the first column. So if you look at this, for any values of k greater than 0, there are no sign changes, meaning that system is absolutely stable. It's an absolutely stable system. Will never have any roots going to the right hand side of the screen. It is as simple as that. So let us move to the next problem. So let me just have a look at. Okay, let me consider this. So you have f of s, which is nothing but gfs is nothing but k into s plus 4 by s plus 0.5 whole square into s plus 2. If I write this, you have repeating poles at minus 0.5, and you have a pole at minus 2, and you have a 0 at minus 4. You have a 0 at minus 4. So this is S-plane representation. And just so now root locus. Okay, how many? Where it will number of loci. Number of loci is equal to how many? It's equal to 3. How many the starting point is? Starting point is origin. Sorry, at minus 0.5, minus 0.5, and at minus 2. Where do they end? The end point is minus 4, infinity, and infinity. Because out of 3, one will go to minus 4, other 2 will go to infinity. Then which part of the root locus is a part of root locus? Then this is not a part. This is not. This is segment 1, segment 2, segment 3, segment 4. Segment 1 is not a part of root locus. Segment 2 is also not a part of root locus. Segment 3 is a part of root locus. Again, segment 4 is not a part of root locus, because if you can see here 1, 2, 3, 4. Here 1, 2, 3. So that's why it's a part. So it actually goes here and then terminates there. And if we can actually find what is that? Asymptotes. Asymptotes are, where are asymptotes now? So asymptotes are how many? So we have p minus z. P minus z, number of asymptotes. Number of asymptotes are 3 poles and a 0, which is equal to 2. So centroid. Centroid means, okay, where does the asymptotes meet? The asymptotes meet at minus 0.5, minus 0.5, minus 2, and minus of minus 4 by p minus z. P minus z. So 3 minus 1. So is it not minus 3 plus 4 by 2? So is it not 1 by 2? But it's on the positive side. So it's here. It is 0.5. Now we know that of course, since you have a repeating pulse at the point 5, the breakaway point, as we know that breakaway point will be minus 0.5 itself. So because there are no other breakaway points expected here anywhere on the real axis. So breakaway point is minus 0.5 itself. It breaks here. Once it breaks, it can't go on this real axis. It can't go in this real axis. It has to be complex. And since you can see there are uh, asymptotes waiting, so it has to follow this. So before we write it, we can actually find the value of k because it has to go to right side. It has to go to right side. The poles are there initially in the left hand side. We have to find the k. We have to find what is that k margin. So for that, it is now what we have to do now is let us write the del of s, which is nothing but s plus 0.5 whole square into s plus 2 plus k into s plus 4 equal to 0. So it is s square plus okay, 0.5 into 2, which is 1s plus 0.5 square is 0.25. 0.25 into s plus 2 plus ks plus 4k equal to 0. So then this will become s cube plus 2s square plus s square plus 2s plus 0.25s plus because 0.25 into 2 is actually 0.5. 0.25 into 2 is 0.5. And of course plus ks plus 4k. Upon simplifying this will become s cube, this is del of s cube plus 3s square plus 2.25 plus k into s plus 4k plus 0.5 equal to 0 is your characteristic equation. Then s cube is square, it is now 1 2.25 plus k, then it is 3 4k plus 0.5. S power 1 will be how much is 3 into 2.25, it is 6.775k, so 6.75 plus 3k minus 4k minus 0.5 by 3 comma 0, then s power 0 is 4k plus 0.5. So this term can become 0. This term can become 0. So what we have now is, okay, now it is 6.25 minus k can be 0. Of course, by 3 can be 0. Therefore, k margin is 6.25. If k is greater than 6.25, then this will become negative, meaning the two sign changes. So now if we can come here, so we know that this one which leaves at minus 2 will terminate at minus 4. The poles which are leaving at minus 0.5, which are breaking at minus 0.5, will pass through this. Exactly what is the point of when they pass through? For that we need to write the auxiliary equation, which is nothing but 3a square plus 4k margin plus 0.5 equal to 0. So then this would be 3a square plus 4 into 6.25 plus it is 25.5 is equal to 0. Then s will be having plus or minus of j, which will be 25.5 divided by 3 under root. That is 25.5 divided by 3 under root of that is S will be plus or minus of J 2.915. 2.915. So now it will cross at plus J 2.915. It will cross at minus J 2.915. Meaning it breaks at 0.5 minus 0.5. It crosses this and then goes along with this. You can see it crosses this. See, now it is symmetric above the real axis. It's going like this. So it breaks at this point and it is going like this. So this is how the root locus is. So what is value of K margin? So K margin is 6.2. It's as per this 6.2. Okay, fine. So this is how we can find. Okay, so we will see a few more problems in the coming videos. Thank you.